Welcome to this lesson on desk checking, also known as hand tracing, programming logic. After studying this lesson, you should be able to desk check an application's code, articulate the benefits of desk checking or hand tracing code from both a design and troubleshooting standpoint and from a pedagogical perspective. Let's explore a classic troubleshooting and design technique known as desk checking. Desk checking is also known as hand tracing because in the classic use of it, in the early days, we had computers that didn't have nice tools like interactive debuggers, and also a lot of times we were on shared time systems, and you may have limited access to, or maybe very expensive to run the computer, and so we would do our programming and then walk through our logic, usually at the point where we had a simple flowchart or pseudocode before we had even created the code, just to test our logic and make sure that we had thought of everything, because of course, the computer, there's no magic. It does exactly what you tell it to do in exactly the order that you code it to do it. And so this was where you would catch a lot of your bugs and save a lot of wasted time waiting for your time in the queue to get back in line to get your program run to see if it ran correctly or not. We still use this technique today, but it's become more of a pedagogical tool for learning and teaching because it helps us to develop the habit of thinking incrementally. Human beings tend to be very intuitive thinkers. We go from point A to point B without really seeming to pass through the intervening space. We have a lot of intuition, a lot of muscle memory, a lot of experience that guides us in understanding things. And so a lot of the computing we do inside our own brains, we're not even aware of the incremental steps. And that's not really very useful when we have to write code. We need to go back to basics and teach our brain to think through steps at a very incremental, very atomic level. Okay, so let's take this simple program as a sample, and consistent with what we would have in old days of just having the flowchart, we would check our design, and we could do it visually, and we'd say, okay, I start my program, and I declare an integer I, and I declare an integer accumulator. The accumulator is initialized. Probably should have initialized I, but the reason I didn't is I'm going to use I in a loop, which is going to initialize I the first time it runs to the loop, and it's going to initialize it to 0. Then it's going to, next time through the loop, it's going to increment to 1, to 2, to 3, and then after 3, when it gets to the exit condition, it's going to increment it one more time to 4, so it will no longer be in the loop. So when I leave the loop, the value will be 4. And then the accumulator in here, inside the body of the loop, every time through the loop, it's going to add whatever the value of I was to the accumulator, which started at 0. So the first loop through where I is 0, 0 plus 0 is going to be 0, and then 0 plus 1 is 1, and the next time through I will be 2, and 1 plus 2 is 3, and so on. At that point, it gets a little bit fuzzy trying to hold everything in your brain. What does my accumulator finally end up at after the loop exits? And that's where something like desk checking can really help, and we'll see how that works out in a minute. And then we have an output message, and it says the loop executed I times the accumulated total is accumulator. Okay, so let's just run this program, and it's a debugged program. It runs correctly, and let's see what it produces. Okay, so it executed, and says the loop executed 4 times, and the accumulated total is 6. And we're using a little trick here because we started at 0 to 3. The loop actually executed 4 times, and we're using the fact that variable I increments one additional time when it exits the loop. So the range within the loop is 0 to 3. The exit condition happens when I gets incremented an additional time, and it's 4. It's out of range, it falls out. 4 happens to be the number of times the loop ran. And so otherwise, if we were doing like, 1 to, I equals 1 to 3, and we wanted to know how many times, or I equals 1 to 4, the exit condition would be 5, which would misreport the number of times the loop ran. So we would then, subtract 1 from I if you wanted to use that expression down here to say how many times the loop ran. But we're leveraging the fact that we started at 0, and so the index is going to be incremented 1 more, which is actually the ordinal number of times the loop ran, so it being 4. Okay, so hopefully you followed that. If not, this is a great reason why desk checking can help you define why does it happen that way, or if it's happening in an unexpected way, why did it happen the way it happened? Because the code does what you actually told it to do, not what you thought you told it to do. All right, so let's do one other thing here, and that is we're going to jump to the future where we have interactive access to the computer in real time, and we have interactive debugging tools. And let's set a breakpoint here, and we're going to use that in a moment to validate the work we're going to do in desk checking. Okay, so we'll set a breakpoint there, and remember, a breakpoint pauses the computer's execution of the program. At this point, we can then hit the run button to resume and pick up where we left off. When we pause it, we can also use a variable watch window to look at what were the value of the variables at that point in time. So actually, this is one of the reasons why we do less desk checking and hand tracing professionally and use it more as a classroom thing, because now we have tools like this. You can actually use the debugger and interactively step through your code, setting breakpoints and break conditions to see what's actually going on when something happens differently than you expected, and very quickly you can usually pinpoint where your logic is not what you expected or intended it to be. Okay, let's use one other feature of Flowgorithm, because again, ordinarily when we're hand tracing or desk checking, we would be doing this before we have created the actual code. And so one of the nifty tools here we have in our source code viewer is we can look at rather than generating code, we can tell it generate our pseudocode. Okay, so pseudocode is meaning false code. It is terse. Generally, if you're in natural language, your first language is English, it would be English phrases that very concisely describe what you want the computer to do, and they're kind of language agnostic. So pseudocode can be written that generally can be translated into almost any programming language, or at least any procedural or object-oriented language. It works pretty well. All right, so I'm going to take this code, and here's what we're doing. Said in a less formal way than the actual code. Declare the integer I, declare integer accumulator, set the accumulator to 0 for I equals 0 to 3. So pretty close to code, but not quite formal code statements. Set accumulator equals accumulator plus 1 in the for loop, and then display the following. Okay, so I'm going to take this pseudocode and copy it, and over here I've prepared a little spreadsheet. And I'm going to take this code here, and let's see here. Let's put it in an empty sheet for a second. And I'm just going to paste it into one column. Okay. And now I've got my pseudocode just as text. I don't like this blank line here, so I'm going to remove it. Okay, so that's nice and tight, and now I'm going to take 1, 2, 3, 4, 5, 6, 7 rows, and let's go back where I've set up my headings and paste our pseudocode in there, and use a little trick to reformat the spreadsheet so it automatically fits the widths. And here's our original line numbering of the complete program: 2, 3, 4, 5, 6, 7. But you notice because we're running a loop, this is not how the program is actually going to execute, because some of these, the loop body, so the code here and the test for, or the incrementer for the loop, are going to run multiple times until the test fails. We're outside of the range of 3, and then we're going to fall out of the loop. So I'm going to take these two pieces, and let's go ahead and cut them, and we'll just paste them down here for the time being. We'll come back to those. Okay. And now what we're going to do is do our hand tracing, or our desk check. And we would do this on an old Quadrille notepad back in the day, but we have a handy spreadsheet, which is an electronic way to do the same thing. And we're declaring variable I, but remember that at this point, we don't know what value it has. It doesn't have a predetermined value. An accumulator hasn't even been mentioned, so it has a unknown value. Let's take this column and format it so, that it's centered. There we go. And then the output, well, there is no output if we don't have an output statement, so we can just leave that blank, or some people like to put in a dash to say, I didn't forget it, there just was nothing there. I'm going to leave mine blank. Okay, and we're going to declare the integer accumulator, and again, it's declared, but it hasn't been assigned any specific value, and so we're going to put a question mark in there. It's ambiguous. We don't know. It hasn't been set to anything. Now, accumulator is going to be set to 0 here, but I still has not been initialized, so that's unknown. And again, no output. And then for I equals 0 to 3, so I now is being set to 0. Accumulator, if it's not mentioned, whatever was in it in the last step persists in this step. Okay, so that's 0. And we're going to set the accumulator, so we're not changing I, so I remains 0. And accumulator is going to be the previous value of accumulator plus I. Well, the previous value of accumulator was 0, plus 0 is still 0. Not terribly exciting. Okay, so now what happens next? Well, now we're back up to running the loop test and the loop body again. So I'm going to take this and paste it in. And now I doesn't get reinitialized to 0 because we're in the loop. So I is now just going to be incremented. I becomes 1. And the accumulator we didn't reference, hasn't changed yet. Here's where the accumulator is going to change. I is unchanged at 1, but accumulator becomes equal to accumulator, which is 0 plus 1 equals 1. And again, still no output. All right, so we're going to repeat these loops, the loop body and loop test again. Okay, and notice, so the pattern of execution, and if we looked at the line numbers, 1, 2, 3, 4, 5, 4, 5, 4, 5. So 4, 5 is going to repeat as often as the loop repeats till we find the exit condition. Okay, and for I equals 0 to 3, so we did 0, we did 1, so now I is incremented again to 2. Accumulator hasn't been changed yet, that's 1. And we set accumulator now is what we're talking about, so I is not going to change, so it continues to equal 2, and so on. And let's see, accumulator is equal 1 plus 2 equals 3. And what is the value of I? I is 2. Is that still within the range of our loop? Yes, it is. So the loop is going to happen again. We'll paste that in there again. And now set for I equals 0 to 3. So now we've incremented I from 2 to 3. And accumulator hasn't changed, so it's still 3. And now we're going to set accumulator to accumulator plus I, and so I is still 3, and 3 plus 3 is 6. And then this next time here, I is going to be incremented one more time, and so the loop is going to end, right? So we've found our end for condition. So let's take these and get rid of these empty lines. End for, now remember that what made it fall out of bed was that the loop test incremented I one more time. So I goes to 4, accumulator's not changed, and then we have to see what we're going to output. So the output statement does not alter, in this case, either of those variables, and our output is going to be the loop executed, and I is now equal to 4, so we put the number 4, it replaces the variable, times the accumulated total is, and accumulator value is 6, and so there's our output, and let's resize everything so that it matches. And so here we have a complete desk check or hand trace of the run from the time the variables are initialized, every time the variable changes, and we can see as we go the pattern it goes through. And in checking this, if we were to end up with an output or a result that is different than anticipated, we should find it in looking at our code here. And again, having forced your mind to follow increment by increment, step by step, how the code works, this is a wonderful way to really become a very sharp programmer. Let's see the modern way. What would we do with the tools we have in integrated development environment? We'll use our Flogoratham teaching and learning tool for that. And you may not have seen this feature yet. So we set a breakpoint here. I said that would be useful. And so let's run it. And the code has now run just to that breakpoint. So the breakpoint is green. Okay, and I have something here with Windows layout. And so let's go ahead and show the variables and console. And so here's our logic so we can see where it is stopped at the breakpoint. And this very first time through, at this breakpoint, I is now 0 and the accumulator is 0. Okay, and there's nothing output to the console. How does that compare to what our spreadsheet said? Well, you know, the first time you run through the loop, in the middle of the loop, so here we are in the body, here's our first for next, and then this is the body of the loop. We expect to see 0, 0, and what are we seeing? In fact, we are seeing 0, 0. What if we run to the next point? 1 and 0. Does that match our desk check? 1 and 0. Yes, it does. Okay. And continue stepping through, and it goes to 2 and 1, 3 and 3, 4 and 6, and then we have an output, and our program ends. Very good. So our actual interactive debugging tools validated what we found with our hand tracing and desk checking. And if you're having problems understanding or really following what is happening with your code, and if you've just been sort of following the pattern, which is not a bad way to learn, but if you're not really understanding what's going on with some of the code, then taking the time to break out a spreadsheet like this and desk check a couple times will help you to understand exactly what your code is doing, where it's doing it, or if it shows using the debugger and a breakpoint that something different is happening, you can see exactly where you're getting a different result than expected, and you can concentrate, focus on that one line of code to understand why is that different than I expected it would be, okay? And so again, we have the line number being executed here, and we have the logic that we're going to execute. This could be, if you've actually got your actual code, you could put your actual code in here. Otherwise, we use pseudocode for the logic. And then we create a column for each variable that we are going to have in our program so we can watch how it changes. While it's in an ambiguous or unassigned state, we have it as a question mark, and as soon as it gets assigned a value, we keep updating that value every time it changes. And then we have an output window that shows the actual output. So here we see the code, which references the variables and whatnot, and here we have the actual result of that code with the variable values replaced with their actual values at that point in the program run. All right, I hope you find that useful. This concludes the lesson.